When I'm having a molecule like this, if I want to name it, I'm going to start to number the carbons that I'm having. And the carbons that I'm having a 1, a 2, a 3, a 4, a 5, and a 6. So I know very well that I'm having hexane. But I'm having a branch. I'm having a branch on the third carbon. So, and the branch is a methyl. So I'm having such a branch, so I can give it a name, 3-methyl hexane. That's the name of the compound for the molecule I'm having. Now, this molecule, I can decide to draw a mirror if I want to depict the mirror image of it. I can call these my molecule A. And after that, I'm going to decide to put a mirror. So I'm going to have a mirror like this. So I want to sketch a drawing of this molecule, how it will be seen in a mirror. So in a mirror, if this is my mirror, the molecule is going to be shown like this. I'm going to have the center carbon still there, but on this side, this is where I'll be having that bond. Then on the upper part, I'll be having a CH3. On this side, I'll be having a hydrogen. Then the wedge will be here. Let me just shade it so that we can see how the wedge looks like. Then that's where I'm going to have that. Now, this is now the mirror image, and my mirror image is going to be my molecule B. It is still just 3-methyl hexane. But now there are key things that we need to know. No matter how I try to rotate compound B or molecule B, I will never get compound or molecule A. However much I try rotating molecule B, I will never get molecule A. Now, these molecules have a center. Their center, a carbon in the center here. This carbon in the center is called chiral carbon. And whenever we have a chiral carbon is just a carbon that is bonded to 4 other groups. Now, 2 molecules which are mirror images of each other are called enantiomers. So molecule A and B, we can give them a name, enantiomers. And the next thing that we need to know, an enantiomer is a molecule or a compound that have the same exact molecular formula, but they are mirror images of each other. So they show mirror images of each other. So our molecule A and B are enantiomers because they are mirror images of each other. Now, the next thing that we need to know, not all molecules are chiral molecules. So when I am having a molecule, the chiral carbon, we call that chiral molecule. But we need to know that not all molecules are chiral molecules. And those molecules that doesn't have a chiral carbon are called achiral molecules. And example of a chiral molecule, I'm going to draw one. The situation where I'm having a C that is bonded to a CH3 at the top. Then I'm having a situation whereby I'm having that bond. Then the wedge is down here. Then on the wedge, I'm having that. Then on the other part, I'm having a bond that looks like that. The CH3. Sorry, CH3. So this is not a chiral molecule because I'm having a CH3 and a CH3. So since these ones are similar, this molecule is a chiral molecule. A chiral molecule. Now, it means that if I introduce a mirror, I will have a situation whereby at the end of the day, I'm still going to form the same molecule, but now oriented in a different manner. So I'm going to have a carbon, then we will have that, then my wedge will be down here, then on the other part I'll be having a CH3, then a CH3 on top. But what makes these molecules a chiral? If I rotate molecule A 180 degrees, I will get molecule B. So it means that those molecules are not chiral molecules and are called achiral molecules. Now, to understand how optical isomerism works, is something that we need to know about optical activity of chiral molecules. We call it optical activity of chiral molecules. And from introduction, there are key things that we need to understand. Light. Imagine we have a sun. This is my sun, and all rays of light are leaving from the sun. Then, what we see is light. But how can we define light? Light is an electromagnetic radiation composed of many photons. It is an electromagnetic radiation composed of many photons. It is an electromagnetic radiation composed of many photons. Now, a single photon of light, so imagine a situation where I'm picking only a single photon. So a single photon of light can be expressed in alternating regions of electric field and magnetic field. So a single photon can give us alternating regions of electric field and magnetic field. If so, then how can we sketch it? So I can decide to sketch that I will have my y axis. This is going to be my x. Then I'm going to have another one. This is called my z axis. So if I want to demonstrate the alternating regions of electric and magnetic field of light, I'm going to draw something like this. And I draw it like that. Let me sketch it in a better way. Yes. So when something like that, we are having alternating regions of magnetic and electric field. So the key thing that we need to know, electric and magnetic fields are perpendicular to each other and are also perpendicular to the direction of the photon. So imagine the photon is going towards this direction. Now, magnetic and electric field are perpendicular to each other. So if I'm having my magnetic field going like this, it means that another oscillation exists that is opposite of this. That looks like that. So the magnetic field is supposed to be perpendicular. Now I'm going to have, if those are my magnetic field, the electric fields must be perpendicular to that. So I'll have them moving towards that direction along the Z. These ones were moving like this. I'm assuming they're perpendicular. Now these ones will move like that. like that, like that. This one will move like that, like that, like that, and like that. So this is a demonstration of how the perpendicularness of the magnetic and electric field as a property of light. Now imagine a situation whereby I want to use a polarizer. So the key thing that we need to know, a single light source releases many photons whose fields are oriented in different directions, the way I showed you here. All these are oriented in different directions. But now I can decide to use a polarizer. Now, a polarizer device is a substance that neutralizes, or I can say it screens out all photons except those oriented in the same direction. So if I subject these to a polarizer device, I'm having photons oriented in the same direction. So if I introduce them to a polarizer device, a device that looks like this, I'm just having a sketch of it. So I'm assuming this is my polarizer device and this is my device. Now from the polarizer, I will have a straight line to show that this is the direction of the photon. Now a polarizer device will give us different oscillations of magnetic and electric field property of light. So I will have a situation now by my light's magnetic field is oriented in that way. Now when a photon of light is passed through a polarizer, we are calling this polarizer device. When a photon of light is passed through a polarizer, we generate a certain type of light known as plane polarized light. Now this one is called plane polarized light. And when I'm having plane polarized light, there's something that we need to know. What is the behavior? What's the relationship between plane polarized light and chiral molecules? Now, in the optical activity, we are looking at the ability to rotate plane polarized light. Ability to rotate plane polarized light. And in the ability to rotate plane polarized light, chiral molecules are optically active. They are optically active, meaning they have the ability to rotate plane polarized light. But how do they do that? If I'm having plane polarized light, for example, this one that I'm going to sketch here, if I'm having a plane polarized light that is oriented in that manner, when I pass it through a chiral molecule, when I pass it through a chiral molecule has the ability to rotate this plane polarized light. And it can rotate the plane polarized light until now the plane polarized light will be sketched in this manner. We'll be having more of a slanting situation where now the magnetic and the electric field are rotated. And the rotation we are having here is, we can assume that it is clockwise rotation. Clockwise rotation. A clockwise rotation. Now, this molecule here is my enantiomer. Then this is now rotated plane polarized light. Now the key thing that we need to know is that when plane polarized light is passed through a molecule, the molecule will rotate that light clockwise direction. Now if an enantiomer rotates plane polarized light in a clockwise direction, we call that enantiomer dextro-rotatory enantiomer. We call it dextro-rotatory enantiomer. A molecule that rotates plane polarized light clockwise is called dextro-rotatory enantiomer, and such an enantiomer is assigned. It is assigned a net positive sign. Now, the other enantiomer that has the ability to rotate the same plane polarized light, same degree, but now anti-clockwise. This is now anti-clockwise. Such an enantiomer is called levo-rotatory enantiomer. We call it levo-rotatory enantiomer. And we assign it, a net negative charge or negative sign, sorry. Now that's what can be gotten in relation to chiral molecules and their relationship with optical activity, which is under optical isomerism. Thank you very much. Have a wonderful time. Let us meet in the next video where I'll be discussing about racemic mixtures.